So today we will see first what is equivalence relation. So as we have seen the three types of relation, reflexive, symmetric and transitive. And if a relation is reflexive, symmetric and transitive, then it is called equivalence relation. So how we will define it, our relation are on set, our relation are on a set A, on a set A is said to be an equivalence relation. An equivalence relation on A if and only if it is, if and only if it is, IFF is used in mathematics for if and only if. IFF means, I told you before also, if and only if. So if the relation is number one, if it is reflexive, if it is reflexive, and what is the condition for reflexive? We can say for all, we can write like this: A, every element is related to itself, A is related to A, or we can write A belongs to R. For all A belongs to A. 1, 1, 2, 2, 3, 3, 4, 4, we have seen the example. And if it is symmetric, we have seen if A, either we write if AB, actually we should write if AB belongs to R, implies that BA also belongs to R. For, not for all, for AB belongs to A. Or the same thing we can write as if here you can write if this and then in writing also if you write if A is related to B, and then B is related to A, or AB belongs to A. So this is the same statement. Either you write in this way or you write in this way. Same thing. It's up to you. You can explain in any way, either using the ordered pair or you can use like this also. And the third one is it is transitive. Transitive means if A, B belongs to R and B, C belongs to R. AB belongs to R and BC belongs to R, then, or implies that same thing, then AC belongs to R or ABC belongs to R. Not all. I told you this is not for all. Oh, it should not be all numbers, but whatever is there. Or we can write in this way also if A is related to B and B is related to C, then either you use this way or then same thing. If then you can use if here and here you can use then, or you can use the implies that if A is related to B and B is related to C, then A is related to C or A, B, C belongs to R. So these three things we have to check. For the question, we have to check. Sometimes the questions are based on some properties. We have to check the properties whether it is applicable or not. And sometimes it is mathematical questions, so we have to check like that only. So it depends on the question. But we should see the conditions, all these three conditions. Okay. So now we can start exercise. Actually, we can start the exercise where we have to show the given relations are equivalence relations. Exercise 1.1, whether each of the following relations are reflexive, symmetric, and transitive. We have to check reflexivity, symmetricity, and transitivity on the given text. So, question number one. Given is set A. First, you check that what are the elements in set A? 1, 2, 3 up to 13, 14. This is the set A. And the relation is defined as R is equal to xy such that 3x minus y is equal to 0. Okay. So we have to analyze what will be the value of R. If we can write easily, we can have the values here. That's better. So x, y both belongs to A, set A. But the numbers, you know that it will have 14 into 14 numbers or 96 ordered pairs. If you write its universal set, it will have 14 into 14. Okay. So 1, 1, 1, 2, 1, 3 like that. That's 2, 2, 1, 2, 3, 2, 4. But we have to check this condition. The condition is y is equal to 3y, 3x minus 3x minus y means y is equal to 3x. Correct? And x belongs to x and y both belongs to A. X and y both belongs to A. So if we take x is equal to, now we can check here, x is equal to 1. When x is equal to 1, y is equal to 3. X is equal to 1, y is equal to 3. That means 1, 3. So 1 and 3 both are in A. So 1, 3 belongs to R. Then you check with x is equal to 2. You put x is equal to 2. Y will be equal to 2, 3 is 6. So 2, 6, 6 is there. 2, 6 will belong to R. Similarly, x is equal to 3. But it is not necessary to check every time, because yes, just in the starting you should keep in your mind that what will be the means, whether it will be reflective or not. So in that case, so then y is equal to, what will be the y? X is equal to 3, 3, 3 is a 9. So 9 is also there. So this pair will also belong to the given relation. Then x is equal to 4 and y will be equal to 4, 3 is a 12. So 4, 12 will also belong to the given relation. But when you will put x equal to 5, 5 is a 15, 15 will not belong. You will put x is equal to 4, y will be equal to 12, 4 3 is a, x is equal to 5, sorry. X equal to 5, y will be equal to 5 3 is a 15. And 15 is not there in that A. 15 is not there in that A. Okay. So therefore we have the relation, if you want to write in this form, the relation is having 1, 3, 2, 6. You should analyze actually relation, then only you can start doing it. we have to check that whether it is reflexive or not. It is looking like 1, 1, 2, 2, 3, 3. It is not there, so it is not reflective. Up now you have two ways of writing. When it is not reflective, you can take one example and show that it is not belonging to R, therefore it is not reflective. Okay? Or you can do it by the definition of this one also. If you will put x, so 3x minus x and 4x is equal to 0, x is equal to 0, and x does not belong to R, therefore it is not reflective. So both the ways are correct. You Okay, so first we are doing the reflective. First check for reflective. So there are two ways. I am just showing both ways. We can write one example. We can give one example is one number which is not belonging to this set, and then that will prove that it is not reflective. We can write since 1 1 does not belong to R. Therefore, R is not reflective. One way of writing it. One example, take one example which shows that it is not reflective. Or we can take the definition. R is this 3x minus y. So let for x belongs to R, for x belongs to R implies that 3x minus x, that will be equal to 0, and 3x minus x, 4x is equal to 0, and x is equal to 0. And x is equal to 0, which does not belong to R. So that means x pair means 1, 1, 2, 2, 3, 3, 14 will not belong to R. Therefore, R is not reflective. R is not reflective. So we have the reasons. We have to write the reason, whether you can write directly or sometimes you have to write the relation and then you can take from that. But you should analyze first. You can analyze easily. You can write the ordered pairs and then you can check. Second thing is symmetricity. So for if we write for symmetricity, let xy belongs to, what we have to show that xy belongs to R implies that yx belongs to R. Okay. So similarly, we can take example symmetric, symmetric. For symmetric, we can take one example. 1 3 belongs to this and 3 1 does not belong to this. Also 2 6 belongs to this, 6 2 not belongs to this. So we can take the example since 1 3 belongs to R, but 3 1 does not belong to R. Therefore, R is not symmetric. R is not symmetric. Transitivity, then transitive. Transitive, we have to check 1 3 3 6. We have to take example of where the two numbers where 1 3 3 6, but 1 6 does not belong to R. So since 1 3 and and 3 6 belongs to R, but 1 6 does not belong to R. Therefore, it is not transitive. It is not transitive. Whenever it is not transitive, we can take one example and we can prove it. And whenever it is reflexive, we can directly write the definition for all that x belongs to like that. Okay. So got it, I think. Next question, where we have to check same thing. Reflexive, symmetric, and transitive. So here the relation R on the set N. Instead of A here, set N is given us. So N is the set of natural numbers. We know that what is N? N is 1, 2, 3, 4, 5, and so on. N is a set of natural numbers. And R is defined as R is the set of the ordered pairs which satisfies this condition x y is equal to x plus 5 and x should be less than 4. Means x should be 1, 2, 3, not 4, less than 4. If it is written x is less than equal to 4, then we will take 1, 2, 3, and 4. If it is written x is equal to 4, we will take 1, 2, and 3 values of x. So x, we will put x here and find y. So x is equal to, when you take x is equal to 1, y will be equal to 1 plus 5, that is 6. So we got 1, 6, both are natural numbers. So 1, 6 belongs to R. And similarly, x is equal to 2, then y is equal to 2 plus 5, that is 7. So 2, 7, both are natural numbers. They will belong to N. Therefore, x is equal to 3 will be equal to y is equal to 3 plus 5, 8. So 3 and 8. That's it only. Because we have to take x less than 4. Now you can check. Therefore, we got the value of R as 162738. 162738. Obviously, 112233 is not there, so it is not reflective. So first condition, reflective. For reflective, all should belong to this 112233. So uh, you can write since 1 does not belong to R, therefore R is reflective. Second condition is symmetric. So for symmetric, 1, 6, 6, 1 is not there, 2, 7, 7, 2 is not there, 3, 8, 8, 3 is not there. So when 1, 6 is there or 6, 1 is not there, we cannot check the symmetricity. So that means we can write since 1, 6 belongs to R, but 6, 1 does not belong to R. Therefore, there is no question of symmetricity. So R is not, sorry, I forgot to write here not. R is not reflective. R is not symmetric. R is not symmetric. Third point is transitive. So for transitive, we should have A, B, and B, C belongs to the 1, 6. There is no 6127, there is no 7 something 38, there is no 83. So we can write that there is no order pair in which 6 as the first element. Same in the case for 2, 7 and 3, 8. In all the cases means we are not having, suppose 1, 6 belongs to R, there is no ordered pair in R which has 6 as the first element. Hmm? So the reason will be same of 1, 6 belongs to R, but 6, 6 with any element. So here we cannot take any element. So we can say that 6, 1 belongs to R, but we will write, but there is there is no ordered pair in R where 6 is the first element. 6 is the first element. Similar cases for 2 and 7. We can write here similarly for similar case is with 2, 7 and 3, 8. Means 2, 7 is there is no element. There is no ordered pair where 7 is the first element. 3, 8, there is no ordered pair where 8 is the first element. Therefore, R is not transitive. So you understood when we are going to show that it is not reflective. First of all, we have to check whether it will be reflective or not or transitive. If we reach to that conclusion, okay, we are not having all the elements 1, 1, 2, 2. So then we have to take one example for not. And if we get suppose one all 1, 1, 2, 2, 3, 3, all the elements is separate, then we are not going to give the example. Just we will write for all in terms of AB, or can write in terms of XY. For all AB belongs to R, implies that A, or for all A belongs to R, no need of B, A belongs to R. Therefore, R is reflective. Means we will write direct definition. Direct definition we can write. That will show that for all elements, this property is followed. Okay. So that you have to remember. R is the relation on the set A. A is the set of human beings. Means all human beings are here in the set A, and R is a relation X, Y such that X and Y work at the same place. Work at the same place. This type of questions are also coming. So here you know that it is reflective. It is reflective as X and X work at the same place. The same person, two persons are same. We can say that X and X work at the same place. If it is valid, we can say X and X work at the same place. So if here what we will do, if X belongs to R, implies that it means X and X work at the same place. work at the same place. So I think you have to rejoin now because it will interrupt our question. I'm going to stop the meeting and I'll